Hey, this is Team Thulium. Join us as we delve into the world of chemistry, particularly the elements that you may be familiar with, and answer the question, do we really need to memorize the periodic table?
They know a lot about chemistry, let Team Thulium explain.
Have you ever seen or used this once in your academic life? Well, pretty much everyone's familiar with this thing, even if they don't know much about chemistry. Well, this is the periodic table of elements. It may seem like a random arrangement of symbols, but behind its intricacy and vagueness at first glance, it hides a beautiful pattern that may lead us to a path on how nature works. In the mid-19th century, wherein the basis of arranging the elements seemed so blurry, knowing that the chemists at that time had only a vague idea of atoms and molecules, and they are still oblivious to the existence of protons and electrons, they thought that arranging the elements based on their atomic mass had been the most sensible and logical way to do it. In 1869, the Russian chemist Dmitry Mendeleev and the German chemist Lothar Meyer independently proposed a much more extensive tabulation of elements based on the regular periodic occurrence of properties. Mendeleev arranged known elements according to increasing relative atomic mass and properties into four vertical groups and horizontal periods. Then, he left gaps and predicted properties of undiscovered elements. We can say that at some point, this arrangement was pretty much a success. However, this early arrangement shows some inconsistency, especially when we base it on increasing atomic mass. Take a look at the atomic mass of argon, which is 39.95 atomic mass per unit, compared to potassium that has 39.10 atomic mass per unit. So, argon is heavier than potassium, but they are interchanged in the modern periodic table. Well, simply because chemists thought that it is illogical to place argon, which is an inert gas, in the same group as lithium and sodium, which are two very reactive metals. Thus, these and other discrepancies led to a suggestion that maybe some fundamental property other than atomic mass must be the basis of periodicity. Which is true, because as time goes by, along with scientific advancement, such as the discovery of subatomic particles and valuable interpretations, these unwrap the fact that the atomic number is the missing piece that solves the puzzle, as it was found that increasing atomic number satisfy a more logical arrangement. Given that the atomic number tells us the number of electrons in the atom of an element, electron configuration of element help to explain the recurrence of physical and chemical properties, which makes the periodic table more interesting.
For this part, after learning about the history behind the fancy rearrangements of the periodic table, we will take another look at different classifications of elements, which also show the relationships and similarities among some of the elements. These orders and clusters enable us to understand the behavior of such related elements and to know their properties and characteristics. The periodic table organizes chemical elements into groups, which are columns. Within a group, elements share identical valence electron counts and valence vacancy counts. This uniformity in both atomic composition and structure of valence shells suggests a corresponding similarity in both chemical and physical properties.
Groups are numbered from 1 to 18. As we move from left to right in the periodic table, there are two groups, 1 and 2, in the S block, also known as the hydrogen block. Following these, there are 10 groups, 3 through 12, in the D block, or transition block. Finally, the P block, or main block, comprises 6 groups, 13 through 18. In the case of the elements in the F block, also called the inner transition block, specifically the lanthanides and the actinides do not receive group numbers. From this point forward, we will introduce you to the groups within the periodic table. First, we have the group 1, known as the alkali earth metals. Group 1 elements include lithium, sodium, potassium, rubidium, cesium, and francium. It's important to note that hydrogen is not considered part of group 1 because it generally does not exhibit the properties and characteristics of the group. As shown previously, group 1 elements have one valence electron, making them highly reactive. The group 1 metals are characterized by low density, soft, and shiny properties. They react violently with water, producing hydrogen gas and an alkali metal hydroxide solution as represented by the formula in the screen. When exposed to air, these metals gradually lose their shiny appearance as they combine with oxygen gas to form oxides, peroxides, and superoxides. Examples include lithium oxide, sodium peroxide, and potassium superoxide. These metals find various applications such as lithium-ion batteries, the use of sodium in common food salt seasoning, and potassium compounds are important components for fertilizers. Moving on to Group 2A, also known as the alkaline earth metals, this group comprises beryllium, magnesium, calcium, strontium, barium, and radium. These elements are reactive, although they are generally less reactive than alkali metals. Alkaline earth metals share characteristics such as low densities, melting points, and boiling points, and they tend to form solutions with a pH greater than 7. The reactivities of alkaline earth metals with water vary significantly. For instance, beryllium does not react with water, magnesium reacts slowly with steam, and calcium, strontium, and barium are reactive enough to attack cold water. The reactivity of alkaline earth metals toward oxygen also increases from beryllium to barium, leading to the formation of metal oxides. Beryllium's naturally occurring compound is emerald, calcium is essential for healthy bones, and plants require magnesium to form chlorophyll molecules used in photosynthesis, and salts derived from strontium compounds are employed in fireworks and signal flares. Next, transition metals are defined as elements possessing or readily forming partially filled d orbitals. These metals can be further categorized based on the electronic structures of their atoms into three primary transition series, namely the first, second, and third transition series, along with two inner transition series known as the lanthanides and the actinides. The first main transition series spans from either scandium or titanium to zinc. The second series encompasses elements from yttrium to cadmium, while the third series extends from lanthanum to mercury. Some transition metals exhibit vibrant aqueous solutions, and the colors of these complexes are elucidated by the crystal field theory. Crystal field theory explains the color in transition metal complexes through the absorption of light causing electronic transitions. While a detailed explanation of CFT is beyond the scope of this discussion, when white light containing all colors shines on a transition metal complex, specific wavelengths are absorbed. This absorption corresponds to the energy difference between two sets of d orbitals. The remaining light, not absorbed, reaches our eyes and imparts the complex with its characteristic color. Next, the lanthanides consist of 14 elements ranging from cerium to lutetium. In the lanthanide series, the 4F sublevel is in the process of being filled. On the other hand, the actinides comprise the other 14 elements from thorium to lawrencium, and in this series, the 5F sublevel is in the process of being filled. All actinides are radioactive, with only the first four occurring naturally on Earth. The remaining actinides have been artificially created in the laboratory. Together, the lanthanides and actinides are sometimes referred to as the inner transition elements. Lanthanides find applications in various fields, including optical devices such as night vision goggles, petroleum refining, and actinides are also valuable primarily because they are radioactive and they can be used as energy sources for cardiac pacemakers. Also, some actinides have been employed in nuclear power plants. Proceeding with Group 3A of the periodic table, also known as the boron family, includes the metallide boron, metals aluminum, gallium, indium, and thallium, and the newly synthesized element nihonium. Boron predominantly forms covalent bonds, whereas the other elements in Group 3A tend to form mostly ionic bonds. These metals in Group 3A possess 3 valence electrons in their highest energy orbitals. And some common properties of Group 3A elements include being soft, silver-gray metals, good conductors of electricity, and having low melting and boiling points. The most common uses of Group 3A elements are first, boron, commonly used in fiberglass making, or the borosilicate glass known as Pyrex, makes the glass heat resistant. Aluminum is used in various applications such as electrical gadgets, construction materials, and even vessels and apparatuses for cooking and packaging for food materials. Now, the group 4A elements found at the 14th column across, they are also called the carbon family since carbon is the first of these elements. It is comprised of carbon, silicon, germanium, tin, lead, and flerovium. They are characterized by 4 valence electrons, and all the group 4A elements have the same general electron configuration for the valence electrons. Carbon, silicon, and germanium tend to form covalent bonds, while tin and lead form ionic bonds. All group 4A elements react with hydrogen, oxygen, and halogens. Three commonly occurring forms of carbon: graphite, amorphous carbon, and diamond, and these are used in many modern products including inks, rubber, steels, pencils, and even more. Group 5A, located in the 15th column of the periodic table, comprises of nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. The elements in the nitrogen family have 5 electrons in their outer energy level, with 2 in the S subshell and 3 unpaired electrons in the P subshell. Nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, and bismuth stands out as a metal. Except for nitrogen, the elements are solid at room temperature. Also, except for nitrogen and bismuth, the elements exist in 2 or more allotropic forms. The nitrogen family elements exhibit a diverse range of physical and chemical properties. Their compounds may be transparent, diamagnetic, or paramagnetic at room temperature and may conduct electricity when heated. Fact: air is made up of approximately 78% nitrogen. Also, nitrogen and phosphorus are 2 of the 3 main nutrients that plants need to grow. Along with arsenic, antimony is commonly used in alloys. Lastly, bismuth is commonly used in cosmetic products and medicine. Moving forward, the group 6A, commonly referred to as the oxygen group or the chalcogens. These are the group of chemical elements on the periodic table that share distinctive properties because of their valence electron configuration. The chalcogen group consists of 6 elements: oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Chalcogens play a vital role in living organisms and industry. Chalcogens are nonmetals or metalloids, and these elements form various compounds such as oxides, sulfides, selenides, tellurides, and polonides. They are very versatile elements as they mainly form covalent bonds with other elements, both acidic and basic compounds. Also, most chalcogen elements have multiple allotropes. For example, there are at least 6 forms of oxygen. Chalcogens have many applications in different industries. For example, oxygen is essential for respiration and combustion, sulfur is used in the production of fertilizers and dyes, and selenium is used in the manufacture of solar cells and electronic devices. Now we're done with the last 2 groups. Group 17 or 7A, the halogens, located on the left of the noble gases on the periodic table, consist of fluorine, chlorine, bromine, iodine, astatine, and the additional element tennessine. Because of the halogen elements have 7 valence electrons, they only require 1 additional electron to form a full octet, and this characteristic makes them more reactive than other nonmetal groups. Halogens form diatomic molecules in their elemental states, and the bonds in these diatomic molecules are nonpolar covalent single bonds. Additionally, halogens readily combine with most elements and are never seen uncombined in nature. Halogens are used in variety of application. For example, chlorine is used to disinfect drinking water in swimming pools. Bromine is used in flame retardants because of its fire-resistant properties. Solutions used to clean open wounds likely contain iodine, and it is commonly found in disinfectant sprays. Lastly, the noble gases, also known as inert gases, constitute a class of elements sharing analogous properties. Placed in the group 18 of the periodic table includes helium, neon, argon, krypton, xenon, and radon are colorless, odorless, and monoatomic gases characterized by low chemical reactivity and stable electronic configurations. In terms of properties, noble gases exhibit specific chemical and physical characteristics. They possess the ability to conduct fluorescence and electricity, crucial for sustaining stability in certain conditions, and are insoluble in water. Their stability is attributed to the presence of a complete octet, resulting in a low tendency to lose or gain electrons. While noble gases generally do not react with other elements, xenon is an exception, as it can form compounds with oxide or fluoride. The elements are used in lamps such as neon lights, in krypton headlamps and in lasers. Helium is used in balloons for deep-sea diving air tanks and to cool superconducting magnets.
Now that the development of the periodic table and the classification of periodic elements has been explained, we shall now discuss the periodic trends. Periodic trends refer to the variations of the properties of elements as one moves across a period or down a group in the periodic table. These trends are crucial in understanding the behavior of elements and predicting their chemical properties. Key examples include effective nuclear charge, atomic and ionic radius, ionization energy, and electronegativity, which illustrate the fundamental principles governing chemical reactivity. So, what is effective nuclear charge? It is often denoted as Z sub F, and it is the net positive charge experienced by an electron in a multi-electron atom. To simplify things, we can visualize it as electrons hanging around the nucleus like bees around the hive. But the catch is that not all of these electrons experience the full force of the nucleus. This phenomenon is called the shielding effect. Inner electrons in an atom partially shield the outer electrons from the full attractive force of the positively charged nucleus. The effective nuclear charge, or Z sub F, is the nuclear charge felt by an electron when both the actual nuclear charge Z and the repulsive effects or shielding of the other electrons are taken into account. In general, Z sub F is given by this formula, where the effective nuclear charge, or Z sub F, is equals to the actual nuclear charge, or Z minus the shielding constant. Do note that the shielding constant is always greater than 0 but smaller than Z. To further quantify and to be able to estimate the relationship between the real number of protons in the nucleus and the effective shielding of electrons in each orbital shell, the Slater's rule can be applied. Furthermore, accurate prediction of electron configuration and ionization energy can be also picked up from this Slater's rule. So how does the Slater's rule really work? First, we must write the electron configuration of the atom in the form shown here. Next, we must identify the electron of interest and ignore all electrons in higher groups. We ignore the electrons in the right side of the listed electron configuration as it does not shield the electrons in the lower group. Two cases for Slater's rule. Generally, the shielding can be experienced by S and P electron, or the shielding experienced by ND or NF valence electrons. They have their corresponding shielding values here shown in the table. Shielding constant is the amount of how much the electrons around a nucleus shield or block the nucleus charge from other electrons. The formula to calculate the shielding constant looks like this, where S is the shielding constant we're trying to find. It's basically the total shielding provided by all the electrons except the one that we're finding. Here is an example. Find the shielding constant for the 3D electron of selenium. To start, we have listed the electron configuration of the selenium here. You can pause the video right now if you want to answer it by yourself and resume if you want to check if your answer is correct. So, first, disregard the electrons on the right side of the electron that we have targeted. After that, search for the corresponding shielding values. For the electrons in the same shell, subtract the electron of interest and multiply it with 0.35. With electrons to the left, add them all up and multiply by 1, and that gives us 18. Get the sum of the products and you will get 21.15. To take it a step further and obtain the effective nuclear charge, we must subtract the obtained total nuclear charge with the obtained shielding constant, and that gives us 12.85. And these extra electrons provide some shielding for the outer electrons from filling the full pool of the nucleus. So even though the nucleus is getting more positively charged, the shielding effect of the inner electrons means that the outer electrons don't feel the full effect of that increased positive charge. As a result, the effective nuclear charge doesn't increase as much as you might expect if you move across a period. Next on is atomic radius. Imagine, you're in a packed room with people standing close together. Each person represents an atom and the space that they take up is like the atomic radius. Every atom has a size to it, kind of like how each person has their own height. That size of the atom from its center to the outermost edge where its electrons hang out is what we call the atomic radius. Now, here's the interesting part. Atomic radius isn't a fixed number for all atoms. It actually varies depending on the type of atom and where it's located on the periodic table. Generally, atoms get bigger as you go down a group in the periodic table. That's because, as you move down, atoms gain more electron shells, making them bigger. Moving on to the ionic radius. When an atom becomes an ion, it changes sizes. So, the size of an ion is from its nucleus to the outermost edge of the electron cloud. This is what we call the ionic radius. But here's the twist. The ionic radius isn't a fixed number for all ions. It actually depends on whether the ion gained or lost electrons and its overall charge. For cations, these are the ions that lost electrons, so they end up smaller than their parent atoms. Meanwhile, for anions, they are the ions that gained electrons, so they end up being bigger than their parent atoms. Like with atomic radius, ionic radius isn't the same for all ions. It varies depending on the type of ion and where it's located in the periodic table. Here's the overall trend. Across a period or row in the periodic table, as you move from left to right, the ionic radius generally decreases for cations and increases for anions. Why? Well, as you move across a period, you're adding more protons to the nucleus, which increases the positive charge and pulls the electrons in closer, making cations smaller. On the other hand, anions get larger because they gain electrons and became more spread out. Meanwhile, down a group or column in the periodic table. As you move down, the ionic radius generally increases for both cations and anions. This is because atoms gain more electron shells, which makes them bigger overall. Summary, the trend of ionic radius depends on whether the ion is a cation or an anion. It changes as you move across or down the periodic table. And also, ionic radius is like the size of an ion from its nucleus to the outermost edge of the electron cloud, and it changes depending on whether the ion gained or lost electrons. This is what we have learned. Let us try arranging these elements in increasing atomic radius. You may pause if you want to answer this by yourself. We've got four elements: nitrogen, sulfur, phosphorus, and chlorine. Now, we want to arrange them in order of increasing atomic radius, basically from smallest to largest. Now, remember, atomic radius is like the size of an atom from nucleus to the outer edge of its electron cloud. So in summary, the order of increasing atomic radius for these elements is chlorine, sulfur, phosphorus, and nitrogen. For another example, let us arrange the elements in order of increasing ionic radius. Again, you may pause if you want to answer this by yourself. First, let's remember that ionic radius depends on the charge of the ion and its position on the periodic table. Also, remember that cations have a smaller atomic radius than that of anions. Through this reasoning, we can deduce that the fluorine anion is the smallest one out of the bunch, followed by the oxygen 2 minus ion and nitrogen 3 minus ion. And the largest is the sodium plus ion. Though an anion, sodium plus is situated lower by the period compared to fluorine minus, oxygen 2 plus, and nitrogen 3 minus. So in summary, the order of increasing ionic radius for these ions is F minus, O2 minus, N3 minus, and sodium plus.
How an element and compound behave is related to its electron configuration. The number of valence electrons of an atom will determine its chemical properties, and consequently, we can infer how stable an atom is based on its ionization energy. Ionization energy is the minimum energy required to remove an electron from a gaseous atom in its ground state.
Think of ionization energy as a quantitative description of how strong the pull of an atom to its electron is. This means that if an atom has a high ionization energy, it will be very difficult to remove the electron from them. We are taught that valence electrons are somehow easy to remove from the atom. However, the core electrons are harder to displace, resulting to a higher ionization energy between the last valence electron and the first core electron. We can observe these ionization energies for lithium.
The trend for ionization energy is it increases as you go from bottom to top in a group for representative elements and from left to right across a period. We can rationalize this trend using the concept of effective nuclear charge. As the effective nuclear charge increases with increasing atomic number, the valence electron will be held more tightly, which will then increase the first ionization energy of the element.
Let's try arranging this element based on their increasing first ionization energy: aluminum, magnesium, sodium, and fluorine. You can pause the video if you need more time. Now, aluminum, magnesium, and sodium belong to the same period, so we can put sodium with the least ionization energy. However, due to irregularity between ionization energies for elements in group 2A and 3A, aluminum will be the next element in line, followed by magnesium, and then the last one is fluorine.
If removing an electron from an atom affects its chemical behavior, their ability to accept electron also has the same effect. Electron affinity is the name of this property, which is defined as the energy change that occurs when an electron is accepted by an atom in its gaseous state to form an ion.
The magnitude of electron affinity of an element also tells us about the stability of the element. Increasing electron affinity also signifies that the negative ion is very stable. Thus, it will have a greater tendency to accept an electron. The sign of an electron affinity also tells us something about whether the reaction is exothermic for a positive electron affinity and endothermic for negative energy.
Electron affinity is measured by removing the electron added in an ion, and since some anions of elements are unstable, this makes it more difficult to measure. We can also correlate effective nuclear charge to electron affinity, hence the trend for electron affinity is the same for ionization energy. This increases from left to right across a period and increases from bottom to top. Unlike ionization energy, it is very difficult and it can be impossible to measure the electron affinity of an atom beyond the first stage because of how it is determined experimentally.
Now, let's try answering this problem. Arrange the following elements in order of descending electron affinity: carbon, nitrogen, boron, and oxygen. Pause the video and try to answer this question. Now, the correct answer is oxygen, as the element with the largest electron affinity here, and followed by carbon, then boron, and lastly, nitrogen. From previous discussion, we already have an idea that a covalent bond may be polar or nonpolar bonds. For example, in HF, electronegativity helps us to identify the type of covalent bond of atoms once they are bonded already. It is defined as to how an atom attracts the electron towards itself during a chemical bond. And since electronegativity is a relative concept, we can only measure the electronegativity of an element during a chemical bond with respect to the electronegativity of other elements.
Generally, electronegativity decreases as you increase the atomic number in a group and increases within the same period. Halogens, oxygen, nitrogen, and sulfur are the most electronegative elements, with alkali and alkaline earth metals as the least electronegative elements. Do note that transition metals do not follow these trends. In this video, we have discussed the history and everything we need to know about the periodic tables, like their properties and the trends. We can now answer the question if we really need to memorize the periodic table. The answer is no. The beauty of the periodic table of elements is being highlighted in the fact that our understanding of the general properties and trends within a group or period can be used to easily predict with considerable accuracy the properties of any element, even though that element may seem to be foreign to us. Familiarization with the trends and properties of element is enough to fully understand other concepts of chemistry.